Now we go on to a special award, which has only been awarded once before, posthumously, to Karl-Heinz Meyer, which is a special Lifetime Achievement Award, and it's been a long time coming, but it's no surprise. This is a picture, by the way, Carver, that I took of you when you were working on his chip design over Christmas, I think, because Carver would always stay behind and finish one whole chip over Thanksgiving or Christmas holiday. So this is a picture that I took of you, Carver, and the jury unanimously agreed that you should be awarded a special recognition of lifetime contribution to neuromorphic engineering for your establishing this entire field, which is now a whole community of people around the world, scientists, technologies, and entrepreneurs to try to take inspiration from the brain to build better electronic systems. And so now to pass it over to Terry here.
So, Carver, we are very fortunate to have you have a vision of what neuromorphic engineering could be someday. And I hope you're proud of us for what we've accomplished. Now, we could have accomplished more, but we're still working. I was a Fairchild Distinguished Scholar at Caltech in 1990, and I had the privilege of being able to eavesdrop on Carverland. So I would come to the lab meetings, and I got to know Toby and others who were there. What a great group. And I really treasure those moments because this is where they argued things out and where the projects were discussed. And it was just an amazing amount of energy and just really exciting to be there. I first met Carver actually at a small workshop earlier. This was in the mid 80s, probably. Carver, I'm not sure if you remember. It was held at in Pittsburgh. It was at a little resort outside of Pittsburgh, and Jeff Hinton organized it. He was at Carnegie Mellon at the time. And, you know, we had 20 people. We were in the basement, no windows. And I remember the first time I heard about the silicon retina, and I was just amazed. And it really impressed me that, you know, that it might be possible someday to actually build a brain that was actually based on physical principles similar to those that nature used. And that was something that has grown and grown since then. Now, so Carver, I remember distinctly having discussions with him. And one of the discussions that we had, we were walking through, it turned out there was a supercomputer convention above us. You know, this is the era of Cray and control data. You know, these are like $100 million machines. And they had actually dancing girls, and it was a different world. But in any case, we walked through it, and he said they don't know it yet, but their time is limited, that they're dinosaurs. And I said, well, they seem to be doing pretty well for dinosaurs. But he explained it. He said, no, Terry, he said, the micros are going to eat their lunch. And they have. And the reason he gave was that, first of all, they're going to get better and better, faster and faster, and cheaper, and they're going to be commoditized because they're commercial products, and they can be millions and millions of, right? So you can make them cheaper and cheaper. And that has come to pass. And so he has not just vision, but he's able to predict the future. And so I'm looking forward to his acceptance speech to find out what he predicts for our future.
Well, of course, it's very special to receive this award named after Misha. And Terry almost got it right. And Toby almost got it right. Actually, the silicon retina was Misha's idea. And she basically dragged me into neurobiology. It wasn't the other way around. She was probably the wisest person I have ever met. And I probably learned more from her than from any other single individual. Incredibly deep thinker. And so I deeply appreciate the fact that Toby and his co-workers have named a prize like this after her, because really she was the one that started this field. And I was fortunate to partner with her in the process. Her view of the field is her thesis is extremely worth reading. It's on the web. And her view was that silicon was a language in which you could express the function of something that worked like neural systems do, that it was governed by limitations that were similar, not identical, but similar. It was a more or less 2 plus epsilon dimensional thing. It was limited in the space you had to build it and the power it took to work it. And so it was silicon. So it made sense to express the function of a neural system in silicon. And she looked at it that way. She also said that once we understood that, it could no doubt result in making useful things. And she also said, that's not my department. And that was wonderful. I should share with you a picture that came out of a visit in the very early 1980s that Misha and I had to Gordon Shepherd's lab in New Haven. Gordon Shepherd had written this book called The Synaptic Organization of the Brain. And we had wonderful, deep discussions with Gordon over about a week in his lab and at dinner and at random times. So I would like to share with you a vision that came out of that trip and the many, many discussions that Misha and I had after that. Every time I've shared this before, people have always nodded and smiled and said, yes, but, and always had all the reasons why it couldn't possibly be true. I'll try one more time. If we look at the representation of information in animal brains of many, many levels of complexity, we find, once we look carefully, that information is encoded at, once you get past the details of the sensory input, the low-level sensory inputs, that representation of events by volleys of neural pulses on bundles of neural processes that then synapse onto the dendrites of receptive neurons. And if you look carefully, the information is encoded in the relative time of arrival of certain dedicated pulses on certain dedicated fibers. Then you look at the decoding of this information, and what you find is, in many cases, not general, there's not, the point has been made that lots of different areas of the brain have different things. Yeah. But in many places, you find that the input pulses make a little excitatory potential in the dendritic tree. And the first thing that was very interesting was that the excitatory pulses from the distal parts of the tree were bigger than the excitatory pulses from the closer in synapses. That is not the property of a passive network. In those days, Rahl had made a basically resistor capacitor network of synaptic, then any kind of neural process, whether it's a dendrite. He had this Rahl model, and everybody believed it couldn't be true because this was a system that obviously had gain. Now, I don't have to tell you that if you have a system as complicated that can have hundreds or thousands of inputs and it has gain, the first thing that's going to happen is it's going to oscillate. So this system must have an exquisite, locally activated gain control system, the most sophisticated gain control system anywhere in any system. And it must be true. So you just think about it for a while. I have these inputs that it's going to recognize some combination of events that mean something. Like there's a leopard about to leap on me, or there's something I could get to eat, but it's going to run away if I'm not quick. And so just think about it for a while. That means that no matter whether it's dark at night and you only get a few photons and you're only working with a few nerve pulses coming into this one dendritic tree, it has to let you know over orders of magnitude of input signal. First lesson of the nervous system. The nervous system does not differentiate gain control from signal processing. That's something we engineers always do. So our engineering background immediately prevents us from seeing the most important principle in the nervous system. But now we're looking at it. And this dendritic tree can decode an arbitrary subset of a pattern coming in. Finding arbitrary subset is a hard computational problem. It's orders of magnitude more effective at that than any algorithm. People for years have been looking for what's the magic in the brain? The magic in the brain, for one, the most magic thing I know is the ability of this system, which uses active gain, exquisitely controlled by the system coming in, non-linearly joining signals that come in with a proper delay to be part of this meaningful volley that's coming down the input. That's orders of magnitude when you're talking about hundreds or thousands of inputs. So I tried like crazy to build one of these things. I couldn't even get one neuron. This was back when I was getting ready to retire in 1990s. And the technology was not nearly as advanced as it is today. Most of the advances that have happened since then have been to make the devices smaller and more digital and less analog. But there must be good ways to build one. And I was delightful to meet people here who are deeply interested in the dendrites as the place where the real heavy lifting in the brain is done. So this was a vision that came out of a visit Misha and I made to Gordon Shepherd's lab and the discussions we had for many years after that. And I'd like to credit that vision largely to Misha. And I'd like to share with you a very deep memories of those discussions. And this award, I hope will be something that we can attach at least one specific deep concept to my relationship with Misha and to this award. Thank you.